All right, deep divers, get ready because we are diving deep into some cutting-edge AI research today. We're talking robots. Robots that can not only see the world, but actually imagine their way through it.
Yeah, imagine like, imagine your robot vacuum cleaner, but it
Oh,
suddenly has like this spatial awareness, like way better than it does now, effortlessly just going around furniture and stuff, and even like
yeah.
anticipating your dog's movements.
Okay,
Okay.
that's impressive, but also maybe a little terrifying. So where's this research coming from?
Well, it's a paper called Navigation World Models. It's from some huge names in AI research, FairEye at meta.nyu, and Berkeley AI Research, and it was just published on December 4th, 2024.
So this is like hot off the presses, and I was skimming the abstract,
Yeah.
and they've created this model that can like predict the future, at least in terms of like what a
Right.
robot will see as it moves. All thanks to something called the Conditional Diffusion Transformer.
Right. Conditional Diffusion Transformer, or CDiT. It's at the heart of their Navigation World Model, or NWM. But maybe we should like step back for a second before we get too lost in the acronym and just like appreciate why navigation is such a hard problem.
Yeah. I mean,
Mm.
we humans do it all the time without even thinking about it. Like,
Yeah.
you can walk and talk and grab a coffee all while like up, dodging slow walking tours. Our brains are like constantly running this simulation of the world around us.
Exactly. We perceive our surroundings, plan our route, adjust to like unexpected obstacles, all in real time. And like
Dang.
replicating that in robots is surprisingly difficult.
And that's where the limitations of like
Yeah.
current robot navigation come in.
Right, yeah.
The paper mentions that. Most robots today
Yeah.
rely on these pre-programmed paths,
And just like
which makes them
things-
really inflexible.
Exactly, yeah. Like, imagine your robot vacuum cleaner runs into a new piece of furniture, or your dog decides to take a nap in the middle of the room. It's totally thrown off because it's only programmed for like
Oh, yeah.
a very specific, unchanging environment.
So this NWM is trying to change all that by giving robots this like simulated world model in their brains.
Yeah, you got it. The NWM learns to predict what the world will look like based on what it sees right now and the actions it takes. It's almost like a virtual reality training ground for robots.
Okay, so that's where the world model part comes in. But what about the conditional diffusion transformer? It's giving me some serious sci-fi vibes.
Well, the CDiT is the type of AI model that makes all of this possible. It's really good at handling these long sequences of data, like a video of a robot moving through a room. And it does this really efficiently, which is important when you need real-time decision-making.
So it's not just looking at like
Yeah.
static images, it's actually learning from videos of
Yeah.
movement and change. That's fascinating.
Yeah, absolutely. And they didn't just use any old videos. They trained the NWM on huge data sets with a focus on real-world scenarios. Like one example is StanD, which is a data set that looks at social navigation, like how people move around each other.
Oh yeah, I saw that in the paper. They also used Tartan Drive, right? Which is all about off-roading. That's a pretty wide range of environments.
Yeah, it is. And that diversity is really important. By exposing the NWM to all sorts of things, from busy sidewalks to rocky terrain, the researchers are trying to create a model that can, like, generalize its knowledge and adapt to new situations.
So it's like giving the NWM a crash course in all the crazy ways
Yeah,
that the world could be.
exactly. Yeah, it's like they're saying to the NWM, okay, here's everything we know about how things move and change. Now go out there and figure out how to navigate it all.
That's quite a challenge. So how do they even begin to test if this NWM is actually learning anything useful?
Well, that's where things get really interesting. They put the NWM through a series of tests in both familiar and completely new environments, and one of the key things they were looking at was its ability to plan.
Plan.
Right.
Sitting down with a map and a compass? I don't picture robots being very good at that.
Yeah. Not with a map and compass, no. But the NWM can simulate different paths in its internal world model and then figure out which ones are most likely to lead to the goal. It's almost like the robot is thinking, okay, if I turn left here, will I get closer to the charging station? What about if I go straight?
So it's not just reacting to what it sees immediately in front of it. It's actually like thinking ahead, considering different possibilities.
Exactly. And what's even more impressive is that it can incorporate constraints during this planning process. Like imagine you could tell your robot, go to the kitchen, but avoid the hallway because the dog is sleeping. The NWM can actually do that, factor in those instructions, and plan a path.
Wow. That's way better than my current robot vacuum. It just seems to want to get tangled in every cord possible. So how did the NWM actually perform in these tests? Did it live up to the hype?
Well, The results were really promising in a lot of cases. The NWM was better than existing navigation models, especially when dealing with those constraints. But like any new research, there were some limitations too.
All right. Let's talk about those limitations. The paper talks a lot about this tendency for the NWM to hallucinate paths, especially in unfamiliar environments. What's going on there?
It's a really interesting problem, basically. When the NWM encounters something totally new, it tries to fill in the blanks based on what it already knows. And that can lead to some pretty wild predictions.
Sounds just like the NWM is being a little too creative with its navigation, like it's making up its own map as it goes along.
Yeah, exactly. It's a good reminder that even with these advancements, we're still early on in developing truly intelligent navigation.
Okay, I'm getting that sense. So we've got this powerful AI that can plan, adapt, and even imagine its way through the world. But it's also prone to these hallucinations when things get unfamiliar, it seems like. There's still a lot to figure out.
There is, yeah. And that's what makes this research so interesting. We're seeing the potential for a real breakthrough in AI-powered navigation, but we're also seeing the challenges that are still out there.
This is definitely a deep dive. That I'm going to be thinking about for a while, but before we go too deep into robot hallucinations, let's take a step back and look a bit closer at how this NWM actually works.
Sounds good to me. Let's do it. Welcome back. So glad we're taking the time to really explore the inner workings of the NWM. It's really remarkable.
Yeah, for sure.
Yeah.
We've talked about this impressive results and, the creative pathfinding, but I'm still a little fuzzy on how it all comes together.
Well, think about those huge data sets that the researchers use. The NWM isn't just memorizing those videos, it's actually abstracting these patterns and relationships between what the robot sees, the actions it takes, and then the changes in the environment.
So it's not just learning specific routes, it's learning the underlying principles of how movement and perception are connected.
You got it. And that's where the conditional diffusion transformer really shines. It can process all that complex visual and action data and turn it into a predictive model.
Okay. I think I need a little more on the CDiT. We keep mentioning it, but I'm still not really clear on what makes it so special for this.
Okay, well, imagine you have this giant jigsaw puzzle, but instead of a static image, you're trying to put together a constantly changing scene. The CDiT is like this master puzzle solver that can not only assemble the pieces, but also predict how the picture will change with each new piece that's added.
So it's like looking ahead, anticipating those changes, just like the robot needs to do when it's navigating. That's a great analogy.
Yeah, and it does this by focusing on the relationships between those pieces, the way they fit together. In this case, the pieces are like the visual observations and the actions that the robot takes.
So the CDiT is learning the rules, the physics of the environment, even if it's never seen that exact environment before.
Exactly, and that's what lets the NWM imagine those paths in those new settings, even if they sometimes lead to those hallucinations.
Right, the hallucinations. It's like the NWM is trying to apply the rules it knows to a situation where they don't quite fit. It makes me wonder, how do the researchers measure the NWM's ability to imagine these paths?
That's a great question. They did these clever experiments where they basically gave the NWM a starting point and a goal in a completely new environment, and the NWM had to come up with a path, but it could only see a single image of that environment.
So it was like showing the NWM a photo of a maze and saying, okay, figure out how to get from point A to point B.
Yeah. Exactly. And to evaluate how well it did, they compared the NWM's paths to these ground truth trajectories, which are like the ideal paths, figured out by human experts.
And what did they find? Was the NWM able to come up with decent paths, even in these totally new places?
What's amazing is the NWM was consistently generating paths that were pretty close to the ground truth, even in those new settings. It really suggests that it's not just memorizing routes, it's learning how to generalize its knowledge and apply it to new situations.
That's pretty impressive. It seems like it's showing a level of spatial reasoning. That's getting close to what we see in humans. But we can't forget about those hallucinations. How do the researchers explain those?
Well, they point out that the NWM is still pretty new. It's like a student learning a new skill. There are going to be mistakes.
So the hallucinations are like growing pains, where the NWM is overconfident and makes a wrong turn.
Exactly. And as researchers keep refining the learning algorithms and showing it more and more data, those hallucinations should become less frequent and less severe.
So it's all about practice. The more the NWM learns, the better it will get.
Exactly. It's a process of continuous learning. And the researchers think As the NWM improves, it will have a big impact on robotics.
I can definitely see why they're excited. This tech could change everything, from self-driving cars to search and rescue robots. Imagine a world where robots can not only navigate these complex places, but also adapt to unexpected things, learn from their mistakes, and even anticipate what we need.
Yeah, the possibilities are pretty amazing, and this research is a big step towards making that a reality. But, like we've been saying, there are still some challenges. The NWM's tendency to hallucinate is a good reminder that even the best AI can still make mistakes.
That's an important point. It's easy to get excited about the potential, but it's important to remember we're still in the early stages. There's a lot of work to do before we see robots navigating as well as humans.
Absolutely. We need to approach these advancements with both enthusiasm and a healthy dose of caution. We need to make sure these systems are developed responsibly, focused on safety and ethics, and the well-being of everyone.
Very well said. It's a topic that needs careful thought and discussion as AI keeps getting better. But speaking of AI getting better, let's go back to the NWM. We've talked about how it learns and its limitations. But I'm curious about the ways researchers are using it to really push the boundaries of AI-powered navigation.
That's a great point. One area they're looking at is using NWMs for something called offline model-based reinforcement learning.
Okay, offline model-based reinforcement learning. I'm intrigued, but I definitely need a translation.
Yeah, it's a mouthful. But basically, it's about training AI agents, like robots, to make decisions and take actions. But in a simulated environment, that simulated environment is important because it lets them learn without the risks of the real world.
So instead of sending a robot out there and hoping for the best,
Yeah.
we can train it in a safe virtual world.
Exactly. And the NWM is key to creating that virtual environment. By using the NWM to simulate things, researchers can expose these AI agents to a ton of experiences, helping them learn faster.
It's like giving robots a virtual training ground where they can try things, make mistakes, and learn from them without any real-world consequences.
Yeah, you got it. And it has huge potential for developing robots that are more adaptable and intelligent.
That's amazing. It sounds like the NWM isn't just for navigation. It's a tool for learning and exploration. It's changing how we think about designing, training, and interacting with robots.
It really is a paradigm shift, and it's just one example of how NWMs are pushing the limits of AI-powered navigation. But like with any powerful tool, we have to use it responsibly and ethically.
I totally agree. Developing AI requires us to think about the impact on society and humanity. But before we go too deep there, let's just appreciate how clever this research is.
Yeah, absolutely. The researchers have done some amazing work advancing AI-powered navigation. Their insights are leading the way to a future where robots can seamlessly be a part of our lives, helping us with all sorts of things.
It's a future with incredible promise and potential problems. It's a
Exactly.
future we have to navigate carefully.
Well said. The journey into AI is just beginning. And as we go further, it's so important to have these conversations about the ethical and philosophical implications.
And speaking of conversations, I think it's time for a short break. But don't go anywhere. We'll be right back. To wrap up our exploration of NWMs and talk about those big questions they raise about AI and humanity. Welcome back, deep divers. We've talked a lot about these navigation world models, from the impressive ways they learn to, those times when their imagination kind of takes over.
It has been a fascinating deep dive, and I think it really shows just how complicated robot navigation is. We don't even think about it. But getting machines to do the same thing requires a deep understanding of, perception, planning, and decision-making.
For sure. And this research is getting us closer, even with all the challenges. But before we wrap up, I want to go back to something you mentioned earlier, offline model-based reinforcement learning. I got to admit, that's still kind of swirling around in my head.
Yeah, it's a mouthful, right? But it's a really cool idea, especially with the NWM. It's basically a way to train AI agents, like robots, to do things, but in a virtual environment. That's created by a model, like the NWM.
So we don't send the robot out into the real world to learn by trial and error, which could be, messy and dangerous. We give it this safe virtual space to practice.
Exactly. The NWM becomes like a playground for robots to learn and experiment, but without any real-world consequences.
It's like a flight simulator for robots. But instead of flying, they're learning to navigate.
Exactly. So let's say you want to train a robot to deliver packages in a city. You could use the NWM to create this virtual version of the city with streets, buildings, people, everything.
So it's not just a static map. It's like a dynamic world
Yeah.
that the
Yeah.
robot can interact with.
Exactly. And you can give the robot goals in this world, like delivering packages to certain places,
Right.
while avoiding obstacles and following traffic rules.
And the robot can just try different things
Yeah.
and learn from its mistakes without hurting anyone or anything.
Exactly. And because it's powered by the NWM, which already knows so much about the world, it's a pretty realistic training ground.
That's incredible. So offline model-based reinforcement learning could really speed up the development of better robots.
It could be a game changer. Imagine robots that can learn to do surgery or explore dangerous places or help with disasters, all in this safe virtual world.
That's amazing. But with powerful tech, there are always ethical things to consider. We're basically making a world where robots can learn and evolve without us directly supervising them.
That's true. As we build these AI systems, we need to be careful about the risks and make sure they match our values. We need to think about how to design them, how to train them, and how to make sure they benefit humanity.
It's a complicated challenge, but we have to face it. The future of AI is tied to the future of humanity, and this NWM research shows us that we have the chance to shape that future, to guide it toward a world where AI helps us.
Well said. As we finish this deep dive, it's good to remember that we're still exploring and discovering. These advancements are just a glimpse of what AI might be able to do.
The possibilities are mind-blowing, and as we push the limits, we need to keep asking questions, challenging what we think we know, and having open conversations about AI.
Absolutely. The future of AI is a story we're all writing.
And that's it for this deep dive. Thanks for joining us.
Thanks, everyone.
Keep exploring, keep questioning, and keep diving deep into this amazing world of knowledge and discovery.
And until next time, stay curious
And keep your minds open to all the possibilities of the future.